Hello everyone, welcome to the CeADAR online Tech Talk series. So for today, we are having a talk from Lucas Pereira, and Lucas is a research fellow of Universidade de Lisboa, and also a data science lead of a smart energy company called Prisma. And today, Lucas is going to talk about his work in the H2020 project on smart energy. And the title of the talk is Energy Monitoring, Storage, Control, and AI in the Wild Experience from a Real-World Demonstrator. I hand it over to you, Lucas.
Okay, thank you. Thank you for having me. So this is going to be a very hands-on talk about stuff that actually happened, is happening today. I have some examples of issues we had yesterday night, so it's going to be fun to talk about them. So about myself, so I have a PhD in computer science from the University of Madeira in Portugal. I graduated in 2016. So my PhD was in non-intrusive load monitoring. I think you guys know the field because Anthony is working on that and he's with you guys. I focused more on performance evaluation, more than algorithms and value proposition of the thing. Why do we need disaggregated data? And also performance metrics. Which performance metrics should be used to evaluate this kind of algorithms? And if we can set thresholds, minimum and maximum thresholds to these metrics. So my keywords, I like to present my keywords are computer science, data science, human-computer interaction. And I use the intersections of these three areas to solve problems of potential sustainability, smart grid, smart built environments, and recently water energy food nexus. So why is that? Why computer science, data science, and HEI? So computer science, because you need to develop stuff, you need to have programming skills and software skills and algorithm development skills. Data science, because data is driving all this thing. And human-computer interaction, because if you're doing stuff in the wilds, you're going to deal with people. And although it's not a topic, it's not one of the topics of this talk, is one of the most important aspects of real-world deployments, which is user engagement and keep them in the loop. So my research lines, I was already talking at the performance evaluation, real-world applicability, value proposition. I do a lot of, because we do a lot of these deployments, we get a lot of data sets. And so we do a lot of data set interoperability. And this talk is going to be mostly about renewable energy sources and integration in smart islands. So I'm a research fellow with Técnico in Lisbon and ITI Larsis, which is the lab that I work on. It's an interactive technologies lab. And Larsis is Larsis would be like a CeADAR kind of thing, but it's directly funded by the Portuguese government. So we have like 4 R&D units, all different. We have an Institute for Robotics, one for innovation and policy research, one for ocean research, because it's also a big thing these days, and interactive technology institutes for human-centered computing. So Prisma, so what's Prisma? So Prisma is a spin-off that I made myself and 2 colleagues in 2015, we co-funded. So this is the results of our PhD thesis. I haven't graduated back then, but my 2 colleagues developed eco-feedback solutions, which is how to provide feedback to people. And I developed a bunch of hardware infrastructures to monitor, to collect data and store the data. And interestingly, what we wanted to sell back then was a NILM system, but we quit really fast because NILM has been out there since the 80s and there's no solution. So we were probably not being able to sell it. So we moved to the clouds, and what we wanted to sell is what we call EnergySpectrum, which is data storage in the cloud. It's very flexible. And the idea is that we take EnergySpectrum and you can integrate a bunch of sources, data sources, And you can easily deploy a bunch of pilots with this stuff, real world deployments, that you don't have to worry about the data management. You just have to get the sensors, integrate, and boom, you're live. So we're participating in 3 EU fund projects. So one of them was the SME instrument, and the other one is Smile, which I'm going to talk about today. We've run to another and we didn't get funded because it's chances of not getting funded are much higher than those of getting funded, but yeah, this is life. So when I talk about myself, and if you read my bio, I say that my research is bridging the gap between laboratory and real world technologies for sustainable development. And the thing is that to bridge this gap, you need to do a lot of live deployments. And I've done a few. And the thing is that things fail more often than desired. So even if you have done 1,000 deployments, you will keep finding issues and it's going to fail on you ever and ever again. So this is just a brief history. This is me in 2010, white hair back then. And back then we did some deployments, and in 2010, the smart meter trend was already there. But if you wanted to buy a smart meter, it wasn't that easy. That was expensive, and you had to be a DSO to get the hands in one. So what we did, we actually did our own data acquisition systems. And the most basic one, we used the laptop, which is on the left. This laptop, we use the sound card to read current and voltage sensors and do all the calculation. Then we provided feedback. If you look, this is glued with Velcro to the breaker box of a house. And then we move forward, because this was a bit intrusive, like you have a laptop behind your door, it's not highly desirable. We went to this building level energy monitoring. So the idea here was we're using a DAC, this is LabJack, which can handle up to 14 channels. And we are able to monitor the consumption of all the houses from a single point in the building. So we no longer have to get inside the houses. We just get the permit to get in the building, we install our stuff and we leave, and this is going. There's also an advantage, we only need one internet point. We don't need to rely on people's internet anymore, which is a big problem with real world deployments, which is actual internet. And then time passed, I graduated 2016, then in 2018, I was back in the business of deployments with project. This is where I started with the water, energy, food nexus. So we look at houses, we look at offices, but nobody cares about restaurants. And a lot of energy going to restaurants, to food. Not these days, because pretty much everything is locked down. But there's an interesting story with restaurants, and it's going to change a lot because of all this Uber Eats and all these new apps. It's changed the way food is done, and there's a big opportunity here for flexibility, market demand side flexibility. So what we did in this project was we went there to monitor water consumption, hot and cold water, aggregated consumption. Then we also monitored the electricity consumption with this e-gauge smart meter. So at this point, after like 8 years later, smart meters are already something you can buy easily. You don't have to do your own. But if you look at this is for a pilot. This is in real world. Who would buy a system that's going to look like this in the end? Nobody, right? And then we also did some experiments with waste monitoring. It was kind of a fail because it's a big problem, monitoring waste, because it's waste and people really are not careful with how they manage the waste bins. And then Smile. Smile was another evolution. So at this point, we have access to smart meters. We are no longer relying in laptops. We are not relying in data acquisition boards. We actually bought Carlo Gavazzi smart meters, and we integrate them with our gateway and integrate them with our system. And we installed a bunch of batteries. So we installed 50 houses in Madeira Island, around 50 houses. And only 5 of them have batteries because this is still expensive. So we only had budget for 5. We selected 5 houses based on their production, solar PV, and their consumption patterns. those that had more access would get the batteries. And we also installed an 80 kilowatt hour battery at the substation level. And we're going to see an example of this later. And the idea here was can we use storage at the substation level to improve the grid stability? So yeah, this is part of SMILE project, started in 2017. I'm going to use a big overview. So SMILE focus in islands, and you might think, why islands? Why everybody's talking about islands? If you look at Cordis, there's like 10 or more projects in islands, and there's a good reason for that, because 1.5 times the population of Portugal lives in islands. There's more than 2,000 islands in Europe, and a lot of them are not even connected to the mainland, meaning that they have to generate all they consume. And normally this is based on fossil fuels, because you need to have a very strong spinning reserve. Because if you don't have that, if something happens, you get into darkness. So it's a big opportunity here for islands. It's a bit cluttered now with a lot of projects in here now. So what about SMILE? So SMILE, we have 3 pilots in 3 islands, Orkney, Samso, and Madeira. Samso and Orkney are pretty small, like 5,000 people. Madeira has around 210,000, 20,000, so it's much bigger. And Madeira is the only one that is actually geographically isolated. So if we make a mess with the systems, we will be in the darkness for a few hours or minutes, I don't know. So this is a big picture of the project. So the 3 demonstrators, and they are equal but different. So in Orkney, there's a big focus on EVs, and especially in domestic heating. This is North Scotland, it's pretty cold there, so heating is a big thing. Then we have also in Samso, they have a really cool stuff, which is, we have EVs, but they have electric boats, and they want to do smart charging for electric boats, which is pretty cool. Madeira Island, on the other hand, we focused on storage, residential and distributions, substation level storage, and we also want EVs. We are trying to do some smart charging of electric vehicles. I'm not going to cover this in this presentation, the EVs, only the storage. So if you ask me what's SMILE all about in Madeira Island, it's about piloting the real world integration of solar powered energy storage systems and smart charging of EV technologies. So we have a bunch of deliverables out there about this project that I'm happy to share after. So in this talk, so this is just a brief introduction. So in this talk, from now on, I'm going to cover 3 main points. One is, how do we evolve a hardware and software infrastructure to support all this stuff, all this data, all these people, and all these different kind of devices. For example, we have 50 households, 4 of them with the battery. We have a restaurant, we have a low voltage substation. There's a bunch of different things here that we need to orchestrate, and how do we do that? Then another cool thing is, how do we do real-time simulations? How do we enable real-time simulations on top of this infrastructure? And finally, this is what I bring a bit of machine learning to the talk, which is how we can use machine learning to our benefit, a real-world application case. So I talked about EnergySpectrum before. This is what as Prisma, this is our product. It's a backend, it's a big data storage technology, and how it evolved. So I'm going to show a slide of the beginning of times. So this is what we have before SMILE, or slightly after SMILE started. We have 2 big parts. We have the OT, which is operational technology, and we have the information technology. On the left, OT is about its hardware and middleware. It's smart meters, it's the gateways, it's storage devices, it's whatever. And on the other side, you have all the databases, all the web services, the load balancers, cache, an alert system that uses Slack. Of course, in the end, this all runs in a hardware. And best thing you can do is that you pray that this server, this hardware piece that holds the IT doesn't break down. because they don't have control of the hardware that's going on. So how did this evolve? So small started, then we started to have a bunch of stuff, and it evolved pretty fast. After like less than 1 year, this is what the system looks like. So now we have third-party devices. So what we have is a storage, which is not ours, it's by this company, Sholta, that we have the storage installed in the houses. And the control of the storage is not direct. So we need to go to a cloud, set the set points, and then they go to the storage, and then they go. So this, there's here a loop with a bit of delay, but this is how it has to be if you want to control storage and if you want to do big stuff like demand response and synchronize different storage devices across households. Of course, then we had to add a new stuff. This is a BESS manager. We need to add support to battery control strategies. And we also added support to digital twins. So we have digital replicas of pretty much everything that's going on, such that we can simulate without breaking stuff. That's important. So this is how it looks like. This is the back end. This is what people see. And our system is based on notions of producers, sources, and devices. So what's a producer? A producer is an entity that sends data to our system. So every single participant of our project is a producer. Each micro producer, the substation is a micro producer. Each producer has several devices. So a smart meter is a device, the battery is a device. And a device has like a communication source. So some devices may send active, reactive power, current. Some other devices may send telemetry data, that's like state of charge, temperature, the capacity, the running capacity. So we connect these three things, and using this, we can easily plug in new devices and new types of sensors to our system. And then probably one of the most important features that we have is the dashboard, this real-time dashboard. This shows us, so this is a bit updated now. Now we have 50, like this is from a few months ago. We had only like 10 to 12 installations, and this is where they are located in Madeira Island. And what this tells us is when bad stuff's happening, like here, we had an issue with one of our participants, which was offline. We have real-time feedback on that, and that's pretty important. Because normally, and this is the sad part, people get used to this, and even if the system is offline, they don't use it anymore. So you have to be yourself to figure out when stuff is happening so that you can act on it. Then we have a bunch of front end. So we have this backend for us, but then we enable a lot of apps. So this is a web app. This is responsive. So if we put this on the iPad, it's going to adjust. And this is an example of what our participants have right now. So they have storage, information of the capacity. They can look at the last 7 days, historic. Here they have, this is a case of a restaurant. They have 3 batteries, one in each phase. You can see what's going on with your storage device, how much you're producing, and how much you're sending to the storage. So this is for feedback purposes for the end user. Okay, so this was deployed in Smile. And now we are talking about, okay, but what about algorithms and storage control, and how do you test that? And then this is where we brought the notion. So the thing is that we had to do hardware in the loop simulations. But to do that, you need to have a very expensive hardware infrastructure. So what we did, let's do it with the actual hardware, which is the smart meters of the houses. So I'm going to focus on this part here in the red circle, which is our digital twins. We have two digital replicas. We replicate the vCloud and we replicate the actual storage devices. So I think this is a big buzzword. Digital twins is being used all over the place. So it's a replica of a physical entity. And what makes this different is that it's connected to the real in real time using sensor data. So they all have the same data stream. They all see the same data. They actuate differently on it, and the outputs you get D dash is going to be different based on your decisions, but the input is always the same for everyone. So what have we done? So we've modeled a few stuff. So we had to model storage devices. So we went out there to find models, the best models, not the best, but at least the ones that you can understand and you can get a grip on. So we modeled the inverter efficiency. So we modeled this after one of a few papers. So what this tells us is that we might think, oh, I'm going to buy the biggest inverter that I can, and I'm good. Wrong. There's a trade-off here. You need to choose the right inverter. Another important aspect is storage degradation, because since you are actuating on your storage devices, it will degrade. Normally, if you read papers, many of them, they ignore degradation and they optimize without having this constraint in mind, which is not very ideal, because if you think about the cost of storage these days, every cent is going to make a difference in the end. So if your battery runs out of charge after 1, 2 or 3 years, then it's no go. So the storage was modeled after Tesla Powerwall. There's like 2 types of degradation. One is calendric degradation based on years. The other is based on cycles. So you need to find the best trade-off. So you don't want to run all your cycles before the end of the calendar cycle, but you don't want to reach the 10 years without running all of your cycles. So there's a big trade-off. You need to look at this. And the other part that we actually replicated was the digital twins, was the API. So we wanted to interact with the API, and we wanted to make sure that we would experience all the hopping, that we had to send a request to a server, and then that server replies to us. We didn't want to do it just direct calls, because this will not replicate the thing. It's very far from reality. What's here is still far from reality, as we will see later, but still it's a step closer. So what do these guys give us? So there are 2 ways to interact with the device. So the API allows 2 different ways. One is a single action. So you just send a timestamp and a set point for active and reactive power. And the thing will run until a new set point appears, or until the battery reaches the limits, the upper or lower limits. So you cannot discharge below the minimum state of charge. You cannot charge above the maximum state of charge. So this is very sensitive to network failures, because if you send a set point and you lose connection to the server, which happens more often than one may think, the set point will be running forever until you gain back control, which can be problematic. So there's the multiple actions, and the multiple actions was designed to actually, you want to set a schedule for the whole day. You can send like 24 or 48 set points. The thing is that the last set point works like the single action, so it will run forever until a new set point is given. So what we did in our system is that the last set point is always 0, is to reset stuff, and you stop and the battery stops, because we want to show you, we want to avoid what we call regret and loss of opportunity. So we had to implement this. This is a close replica of the cloud that's actually there to the real batteries. And then we did a bunch of simulations. So this was like 1 year ago, when we still didn't have the batteries. And here is an example of what we call loss of opportunity. So in this case, we had a network failure. The internet failed for some reason, like we stopped getting data from the smart meters. And what happened here is that at this time, 521, the consumption was 143 watts, and the system was able to set the battery. Okay, I have it, I have capacity, I'm going to discharge this amount. So we are not, so the grid, so you're not consuming from the grids. You're, at this point, you're self-sufficient. But then the system fails. And what's happening is that since we sent a single point, this will replicate until we find a new set point. What happens is that if you look here, consumption is increasing, right? And you're not able to update the set points. This is why we call it loss of opportunity. You had the opportunity to consume from storage and you couldn't. This then can be translated into money based on your tariff. If it's a single rate tariff, it's not a problem. But if it's a multiple rate or dynamic rate tariff, then you have a problem here. Of course, that it's not always a problem to lose internet, because sometimes, that this case here, okay, we lost the connection, but the state of charge was already on the 20%, so we couldn't discharge anymore. But if by any chance we were producing more than you were consuming, this would represent the loss of opportunity, because we would be losing the opportunity to store the excess energy. So this is the concepts of that I was talking about, why it's important to set up the right way to interact with the battery, because of these two aspects. So here I have two examples. So this is the real thing. This is a screenshot I took the day before yesterday or yesterday, I'm not. Then I have here replicas from, this is one of our participants. On the left side, I have the digital. On the right, I have the real thing. And you see, they are different, right? Although we set this, we have the same capacity, the same inverter, the behavior is different. If you look at the digital, it's perfect. It's off grid almost for 24 hours. So this is what we want. But if you look at the real thing, we had an issue here at 6 because for some reason we lost communication with the house, and we sent a set point of 1,500 to the server. And since we lost that, we don't have data points from consumption. So at this point, the consumption of the house, the production is 0, the consumption is 0. So I'm going to try to get as much from the battery to compensate for that. So I just put the set point to 1.5, and until I get the points back, until I get a connection established, I'm going to drain the battery. Of course, this is what we call regret, because it's not my fault. It happened because of a network failure, but all this energy is injected in the grid for free, because in Madeira we have it's almost for free. In Madeira we pay 16 cents to buy, and we get around 3-4 cents to if we sell. So it's not a good business, right? And then again in the evening it starts charging again when we get sun. And if you see, it's also different, because in the real thing we had to set a hard threshold, because to avoid that, that the sun is not a thing that you can take for granted. So to avoid the moments where you have a drop in production, we set the limit based on the expected production. In this case was 1.5 kilowatts of maximum that we would get to the battery every instant in time. So I have another example here. And this is from yesterday, and this is another case, and I'm showing the last 7 days. And here we are doing different control strategies. On the digital, we have a greedy with pre-charge. What this is doing is, in the evening, it charges to a capacity. In this case, it charges for 60% of the capacity, which according to our algorithms is enough to cover the morning part. And the other one, we are doing the greedy. The real one is the greedy because it doesn't pay off to do pre-charge, because if you have single rates, greedy is optimal. So we didn't have to, we will not implement this in reality because it doesn't make sense, because in the end, money-wise, you get the same. So, but here there's a big problem, and I think that for some reason, and we don't know yet what happened, the real battery stopped discharging. There's a bunch of points in time where the set point, we have the logs, and we say discharge now, and it's not, it's charging. So got stuck. So there's an issue here. It's either on an our algorithm, it's on the communication, but then a reboot solved it. We reboot the system and it starts working again. So this is the kind of issues that we get in the real world, where things have in the lab, you run for 1 hour, 2 hours. Here, things have to work for 24/7, and it's complicated. So now I'm going to go to a bit of storage control and machine learning. So this is another objective. So the other one is, okay, let's give storage to people and let's try to make them more self-sustainable, increase the rates of self-consumption and self-sufficiency. At this point, what you're going to do is we're going to work at the substation level. And our objective is to use the battery has a value proposition for the DSO. So here's our context and objective. So what in the project, the beginning of the project, we selected the substation with the highest number of microproducers. This is a quite big substation with 250 kVAs. If you consider that you only have 100 consumers, this is a lot. It's got like, you need to consume a lot to reach this level, so you will never reach. And what's interesting here, and what makes this an interesting challenge, is that what you see here is not the demand of all the consumers, is the demand, but also with random solar production. And we don't have access to this data. These guys are selling, injecting in the grid, but we don't know how much. So this will be a problem when we will try to forecast this kind of stuff. So, but simply put, what's our objective? So our objective is to flatten the load. So what we need to do is find the optimal thresholds that we can use the storage to put the load within these bars. Because if we do that, and you manage to do that, you can reduce the spinning reserves. You don't need to produce all this much, because what's happening now is that since there's a chance that you will reach 60 Ks, you have to produce 60 Ks. You need to guarantee, even if you're not using 60 Ks, like in this day, you still have to produce that. So it's a waste of energy. If it's not consumed, it's waste. So we have the battery of 80 kilowatt hours. Actual capacity is 56 kilowatt hours because of the limits. So we have this upper and lower limits. We have the 30 kilowatt inverter. So if you look at the 30 kilowatt inverter, this was not a random value. This is chosen based on average daily load, 27 kilowatts. So if the average daily load is 27, means that we might need to inject at one time 30 kilowatts. But so this is where inverter power is not a random choice. It has to be done based on load analysis. So we propose an algorithm. This is what we are doing now. We are running this actually and trying to deploy this in the next couple of days. So what we are doing is every X minutes, this can be whatever you want. It's bigger than one because we have noticed that our system, the VBESS, takes about 1 or 2 minutes to respond to requests. So every X minutes, at midnight, every day at midnight, we need to find the thresholds for the next 24 hours. And we set as an objective, because of storage degradation, is that we need to get 1 full cycle per day. What's a full cycle? Is that you fully discharge and you fully charge in a day. So you discharge 56 kilowatt hours and you're able to charge the other 56 kilowatt hours. So once this is done, you go back to the main algorithm and you have to calculate the set point for the next x plus 1 minutes. So now you have the thresholds, you know how much you're consuming or you think you know, and you have to adjust the battery to store or to inject based on that. The objective is that the net load, which is demand from consumers plus battery, is inside the two thresholds. Of course, then we just submit the storage and we wait until it's submitted. Then we sleep until the next 5 minutes and we start. This is running in a loop 24/7 until something breaks. So this, at this point, this is not deployed yet. This is only simulation based, but we can already think that where we are going to do some machine learning. So we need day ahead forecasts and we need short-term forecasts. And this is where we are putting some machine learning in place. So we start talking about the data. So what data do we have so to do these forecasts? So we have historical load demand. So we've been monitoring this substation for almost 2 years, since February 2019. We have some gaps in data because of network failures. The minimum resolution that we have is 1 minute. Then we had to buy irradiation data. We need irradiation because since we have a bunch of micro producers, we bought it from solcast.com. It's not very cheap. It's actually pretty expensive, but you gotta do it. So we bought 2 years of data with a minimum resolution of 5 minutes. And then what else do we need? So we are forecasting the consumption of the next day. We need to take account how much solar production will be, but we don't know that. The best that we have is a forecast. So we also have forecasting global horizontal irradiation. But here the minimum resolution is 30 minutes. So this means that all our day ahead operations will need to be done in 30 minutes intervals. And you already can see a problem here because we are doing forecasts based on forecasts. So one of our variable is a forecast. And if you can look at the chart on the right, you have the historical and the forecasts and they don't match. And this happens quite often. So whatever the forecast was, the historical data is not going to be the same. It follows the trend, but it's not the same. And on top, you can see for this data, what the thresholds were. So what have we done? So we've tried a few stuff. We've tried really basic stuff like multi-layer perceptron and support vector regression. But because of this variable of the low of the solar radiation, we were having big problems in actually getting it to work. So we tried deep nets. So since we have all this data, 2 years of data, it's a bunch of data. So what we did, nothing fancy, we just get the sequence based on GRUs. We've tested with this sequence sizes. The best results were for 2 days before and 1 day ahead. So it's 96 samples to predict the next 48. And the features that we are giving, this is all. We have our original features and features that we've created. So the main feature is the load, we scaled it, and G, the global horizontal irradiation. So, and that we have historical, and the D is for the day ahead, because we have that also. And then we have the weekday. Interestingly, this improves performance quite a bit. I wasn't expecting, but it actually does. And then we created some features based on the combination of the loads and the actual radiation. So in this case, what we do is we multiply the loads with the radiation. What this is going to say is that whenever radiation is 0, the load will maintain. And then we subtract the load from it. So the idea here is to give to the algorithm the effect of the radiation in the actual load so that he tries to learn what's going on. So the details, I'm just, to be honest, I'm just learning all this stuff right now. And this is a lot of trial and error. So I just did this very basic sequence to sequence with one encoder, batch normalization, repetition for 48, and then the decoder, time distributed, and the dance. So this is just the standard Seq2Seq GRU implementation. It's not fancy. What I'm trying to put here is the right features to get decent results. So how did we train this stuff? We trained this with almost 2 years of data. We just put data, everything. We dropped none and nothing else. We dropped the not the numbers and nothing else. What's nothing else? I've tried to do data cleaning. I was dropping every day that's not complete, I would drop it. But then I would drop like 20% of the days. And interestingly, the performance would decrease. So these things, they want data, and sometimes it's better to have a little bit of, if it's not too bad, it cannot be the worst data in the world, but it's better a lot of data with some noise or some missing, some fails in the sequence, than little data all clean. So we run this for 1,000 epochs with 100 patients. So this is all standard for this regression problem. And this we tested with 1 month. We tested in September, which is, why September? First of all, this is the last data that we got, but September is also interesting because it's a transition between summer and fall. So you get hot days, you get a lot of not so hot days. So it's really hard to, it's a very good month to actually get the performance, because you get a good balance of what you will see in the year. Our metrics are the root mean squared error and the normalized by range. And here I have some screenshots. True is the ground truth and orange the prediction. And we can see that in some days, the prediction is much lower, because what's happening here is that it thinks that it's going to be, the forecast is a sunshiny day, but in the end, the sun is not shining, so the actual consumption is going up. So some days, so it's pretty decent. We have the matrix here on 24-hour intervals. So we have an average error of 5 kilowatts. So if we think that the range is around 60 or 70 kilowatts, that's an error below like 7%, which is, if you look at literature, is very acceptable to this kind of works. Acceptable to write a paper. We will see that maybe to our purpose is not that acceptable. So, and then we also did short-term forecasts. And at this point, I tried to replicate the other network, but the results weren't that good. So we just used a Seq2 point that was developed for other purpose, and we just retrofitted here. So what we have is 1 minute load. So we use data of 1 minute. We input 1 hour, and we want to forecast the next minute. And then if we want to forecast 5 minutes, what we do is we forecast the next minute, we take the forecast and we push to the array and we forecast the next minute. So after 5 interactions, we are forecasting with 4 forecasted values, which may be complicated. This is why I wanted to do Seq2Seq, but Seq2Seq did okay for a day ahead, but for 5 minutes or 10 minutes, it didn't give good results. So this is actually better. And then the features are the loads, and ironically, it's not even not normalized. The sinus and the cosinus of the load. And this is the performance. If you look at these features, I think this is too good to be true, because you're not giving them a lot, right? And it still manages to do a very good job. So you have days that you have marginal errors. So you actually can guess all the points in one day. So this is pretty good. It's better than I thought, to be honest. It's very good. It was trained with about 6 months of data. It's not even a year long of data. So I was very impressed with this Seq2 point. So some results. About simulations, so this is for 5 minutes and 7 days. On top, we have the original load and the load after. In the bottom, in the middle, here you have the actual forecast. In green is the day ahead, orange is the short term, and you can see that the short term does a really good job in following the actual demand. Then here we have the state of charge of the battery. So what's going on if you're charging, discharging? You will see that some days we don't charge enough to lower the peaks. So if you look here, we managed to bring the consumption down, but it's not inside these intervals. Why is that? So one of the reasons is also because of the forecasts. So normally the day ahead is overly optimistic. So it thinks that it's going to be a lot of sun and that you're going to have a lot of energy to store. So the set point, the lower threshold is set in a way that when you go to the real thing, you don't have enough energy to store in the battery. So you don't get a full cycle. So here you only get up to 60%. Although here you get to the 90%, and this is where you see the best results. But then again, another problem is that when you discharge and you set your set point to 30 kilowatts, which is the maximum, you discharge the battery really fast. So at some point, the algorithm is telling, okay, you need to discharge, but you don't have enough charge, so the load leveling is gone. And we also did this for a 30 minutes look ahead. So this is the same, but instead of every 5 minutes, we do it for 30 minutes. Results are pretty much the same. The only difference is that the set points are smoother. Like we don't have 30Ks anymore. We have like 20Ks. And the result is that you end up having a bit of energy to accommodate these points. But still, those 8% accuracy in day ahead forecast are not good enough for this kind of stuff, right? Also, the algorithm is not fantastic, so we need to work on that as well. But so what? So what is that? Load leveling depends heavily on the quality of the forecasts. So, and there are two options. So there's an option one, which is for computer scientists and machine learning people, is that let's make better forecasts. Let's try seasonality, which probably is going to improve. Let's try ensembles. Let's try some hybrid machine learning. Let's run a bunch of models and create another model that tells you which model should trigger every day based on the season, based on the forecast, whatnot. Option two is most like electrical engineers, and they say, what the heck, let's just assume this is not better that we have and let's live with it. And then we start to do different strategies. And one strategy was what we will do next is update the upper and lower bounds several times a day. Instead of doing it only 24 hours, we will do it, since we have access to this actual data in real time, because we get from the West Solcast, we can get the forecast, the predictions for the day ahead predictions every 6 hours. And at this point, there's another advantage. We can use a receding horizon, which is instead of getting the whole day at 6 a.m., instead of getting 24, the next 24 hours, we only need to get the next 18 hours. So if we should get better results. We should. I'm not, because from my past experience, we're actually getting a bit more noisy results, but this is something to try, which is updating. This is what, if you look at the electrical engineering papers, this is what they do. They get the forecasting and they make the best that they can do with that. And what's the truth? The truth is actually, maybe electrical engineers are right, because the truth is that predictions tend to become harder. So with EVs and self-consumption, this curve is going to be even more random, because if you charge EVs, it's not like you drive them all the same way. So it's going to be a more load in the grid. So this is going to change the game. A lot of randomness there. And of course, that our algorithm is very basic. It's just an heuristic. We need to do much more advanced. And it's actually, this is real-time work. We are actually doing this now, and we want to deploy it as soon as possible, probably during this month. So it's, let's say, happy days ahead. So to sum up, so evolving a hardware software infrastructure is about software skills. So you need to know your software more than hardware. And because for hardware, you just have to pray to God that it doesn't break. So if you have a bunch of Raspberry Pis, and you just have to pray that they don't burn, that the SD cards are good quality and that stuff happens. And then internet issues is, if you rely on people, you will have all sorts of issues. The most common is that they change their internet password and they don't let you know. Then you have to go there. Madeira is okay, but if it's a bigger place that you have to travel for 4 hours, then it starts to be problematic. Another one is digital twins are not Siamese twins, so one might think that they will be a perfect replica. They're not. And it's not because of the digital twin, it's because of the physical twin, because that's a lot of hardware and communication issues that's gonna change how the real thing goes. So you would have to, if you want to have if you want to have a Siamese twin or close to it, you need to actually simulate hardware and communication issues. You need to put this into game or consider those issues in your twin, which is probably not, it's not probably that very easy to do. What happens is that if you think on your theoretical expectations, the digital twin actually does that for you. Okay, so the last thing is day ahead forecasting errors under 8% would be good. So if I'm writing a paper for with this, with real data, a real use case, and I report 8%, 6%, I might get good reviews. But then if I go to the real world, these 8% are not good enough. Maybe there's a model there that has an error of 12% and does a better job because it makes the errors where it's not problematic. So this is a case for performance evaluation, so that we cannot, in real world, the metrics cannot be the traditional machine learning metrics. We need other metrics to actually work on. Okay, so this is it. So thank you. This is what I had for you. This is what happened to me a few days ago. So our Slack, everything was offline because we didn't renew our SSH certificate. So this also happens in the real world. So